Let's now consider the number e. In class, we presented 5 different definitions of the number e. We'll consider in this video just 3 of them. First off, we define the number e to be defined so that if you take the area under the curve, y equals 1 over x, then e is defined to be the number so that the area under the curve is exactly equal to 1. So that the natural log from 1 to e, or the integral from 1 to e of dx over x is equal to 1. So that's your first definition based on an area. The second definition is that we can write e to be equal to the limit as n goes to infinity of 1 plus 1 over n to the nth power. And the third definition is that e can be written as the summation from n equals 0 to infinity of 1 over n factorial. Now, these 3 very different looking expressions turn out to be logically equivalent. The first expression here basically is saying that e is defined so that the natural logarithm of e is equal to 1. So let's take that one as our starting point, that the definition of log of x is equal to the integral of 1 over x. The second one, if I were to evaluate this, this is something that can be evaluated with L'Hopital's rule. So this is the limit as n goes to infinity of e to the n times the logarithm of 1 plus 1 over n. And let me rewrite that as log of 1 plus 1 over n divided by 1 over n. Now, this has the form 0 over 0. Logarithm of 1 plus 0 is 0. 1 over infinity is also 0. And so by L'Hopital's rule, and also by the continuity of the function e to the x, this is equal to the limit as n to infinity of the derivative of the top is 1 over 1 plus 1 over n squared minus 1 here, times the derivative of the inside, which is negative 1 over n squared. Then divided by the derivative of the bottom, which is also negative 1 over n squared. And then it has to be e to this very large exponent. So that's equal to e to the, now this simplifies quite a bit. Negative 1 over n squared over negative 1 over n squared cancels, and so we get e to the limit as n goes to infinity of plus 1 over 1 plus 1 over n squared. As n goes to infinity, this goes to e to the first power, which is e. And so if I know the calculus properties of e to the x, that the derivative of e to the x is itself, and also that because it has a derivative, e to the x is a continuous function, so using those properties from the definition of a logarithm, we get this second definition of e, which stems from basically the considerations of finding the formula of continuous compound interest from the formula for discrete compound interest. Okay, now the third formula, summation n equals 0 to infinity of 1 over n factorial, this comes from the Taylor expansion that e to the x is equal to summation n equals 0 to infinity. So if I write this as f of x equals e to the x, this is equal to the nth derivative at 0 divided by n factorial times x minus 0 to the n. So this power series expansion centered on 0. Because e to the x is an analytic function, e to the x is equal to its power series expansion. Now the derivative of e to the x is e to the x. If I plug in 0, I get 1. So no matter how many derivatives I get, the derivative of e to the x is e to the x. Plug in 0, you get 1. And so this simplifies as summation n equals 0 to infinity of x to the n over n factorial. And then plugging in x equals 0, or plugging in x equals 1, pardon me, gives the third series in red. So these three very different expressions look exactly this, or give the exact same thing for E, even though one's in area, one deals with interest, and one involves a power series.